Good morning. Today I will be presenting a novel approach for finding missed optimizations in compilers. And by missed optimizations, I mean cases where one can reasonably expect that a compiler optimizes a piece of code, but in fact it isn't. Before I explain the actual approach and how we build our tool, let's take a step back and look at the bigger picture. As compiler developers, the goal is to build, obviously, the perfect compiler. But what is this perfect compiler? What are its properties? I guess everyone can come up with a different definition, but probably there are a few things that we can all agree on. The perfect compiler should be correct and robust. It shouldn't miscompile code, it should reject incorrect code, it shouldn't crash, and it should handle gracefully all edge cases. And in the past years, there has been a lot of research on how we can build tools to help us achieve these goals, to make sure that the compiler is correct and it doesn't crash, for example. And works in this domain include things like csmith or creduce. These are tools for generating, randomly generating C programs to stress test a compiler, and methods to reduce these programs to small test cases, a few lines of code, like 10 lines of C code, for example, so that they are understandable and actionable. Other approaches include EMI or Alive2, which are being actively used today to validate transformations, to find crash bugs or miscompilation bugs, and so on. So there is already a lot of know-how on how we can build tools that help us find cases where a compiler is incorrect. But there are other requirements from this perfect compiler, namely performance. And by this, I don't mean that the compiler should be fast, obviously it should, but that the code that it generates should be fast. And in certain domain-specific problems, nowadays machine learning, for example, or linear algebra, there has been a lot of research on how we can generate very efficient code. In some cases, we can even reach something that is really close to the theoretical peak performance of a machine, so essentially as good as it gets. But compilers like LLVM have to perform also very general optimizations, such as jump threading or various loop transformations or constant propagation. And there are a few questions here. First of all, how can we find new transformations or new optimizations? And ideas here include running a super optimizer to find new inst combine rules, for example. But then the mirror problem is, for the existing ones, how do we test them? And by testing, I don't mean for correctness, but whether they behave the way we want them to, whether our constant propagation paths can actually propagate constants in all cases that we care about, or if our new inst combine rule does not cause some problem in a downstream path after it. And in our work, we wanted to fill a gap in this area and provide tooling to help compiler developers work towards this maybe unattainable goal of the perfect compiler, but still a goal. So problems or problematic cases that we find include examples such as this one. Here we have a very simple piece of code with a single global variable a that is initialized at 0, and it's also static, meaning that no other code has access to it. No other code can read to it or write from it. Well, the other way around, read from it and write to it, except for main. And what main does is it first checks, is a non-zero? If it is, it returns 1. Else it writes 1 to a, and then returns 0. Now, the important point is that when if is executed, a can only ever be 0. Therefore, the return 1 is dead. It can never be executed. And also this write to a equals 1 is a dead store, since we don't use a afterwards. So it's not unreasonable to expect that a compiler will optimize this to essentially return 0. Now, if we use Clang, the latest version, or GCC at 0.3, they completely fail at optimizing this. They generate statements or instructions for pretty much every statement that we see in the source code. And in this particular case, probably the problem is that there's one or more analysis passes that are not flow sensitive, meaning that in the path of execution that goes through the if statement, the compiler cannot figure out that a is constant. But interestingly, if we replace the write to a, so this a equals 1 with a equals 0, LLVM does the right thing. GCC is although still struggling. So finding such cases is important not only for understanding the capabilities and limitations of a compiler, but also for improving it. Maybe we want to find edge cases that we're not supporting that we're interested in supporting, or by finding regressions and fixing them, or ideally preventing them from landing in the compiler in the first place. And in our work, we developed an approach for finding these fully automatically. So our tool that is available on GitHub can search for these test cases, and in the end it generates small examples such as the one that I just showed. And the way it does this is by using dead code elimination. I will explain shortly why and how. And we used our tool to report a number of issues on the LLVM's bug tracker, around 50, most of which were confirmed and around a third fixed. So these are not obscure cases that nobody cares about. And for this, we mainly focused on the latest versions of LLVM. So most of these are, we tested 13 and later. And if we started testing for, when we tested for older ones, we actually found hundreds of regressions, each of them with an individual commit that caused them. But I'll come back to this later. And our approach is compiler agnostic, so the numbers on GCC are similar. So what is this lens of dead code elimination, and why do we use it? So DC is a transformation that removes code that can either never be executed or whose execution does not affect the program's behavior. So the important thing is that by removing dead code, we simplify the remaining alive code. So downstream passes have an easier job at transforming or optimizing the program. At the same time, DC runs multiple times, so these downstream passes will also affect DC, and there are others that run before it. So DC is in this nice position that it affects many other passes, so it's really important for a compiler to remove dead code to simplify the job of the remaining components. But it is also affected by many of these. So our core insight was the following. If a compiler is able to remove dead code successfully, then maybe this is a sign that something else has been done correctly. So maybe our alias analysis is doing a good job. On the other hand, if DC somehow fails to eliminate a piece of dead code, maybe this is a sign that something else has gone wrong in some of the other compiler components. And this is exactly our core insight that we use to develop our approach or our tool. And combined with a second observation that if we use different compilers, sometimes they eliminate different dead parts of a program, we can use these two observations to find missed optimizations. But the question is, how do we do this? So if we take an example here with a simple C program with two if statements, and we look at the outputs of two compilers, so here GCC and LLVM, and here I show the outputs as control flow graphs, what we would need is to figure out, is there something that, for example, LLVM eliminated that GCC didn't? And we cannot directly compare the structure of the control flow graph outputs because maybe the two compilers just emit the same code that does the same thing, but through a different structure or a different way. Ideally, what we would want is something like this, to have a mapping that, and to know that these purple basic blocks correspond to the second if statement, and if the red basic block in GCC corresponds to the first if statement. And now, if we had this mapping, we would be able to deduce that something is missing from LLVM, therefore it eliminated it. And GCC has missed this, so it has missed an optimization opportunity. And that's it. That's the main idea. And by doing this, we can find problematic cases in a number of different transformation and analysis. In loop transformations, in jump threading, in various peephole optimizations, in various analysis, and so on. But now there's a challenge. How do we actually figure out what has been eliminated? So if we look at the same test case, but with the actual assembly code, what we would want to figure out is what is the correspondence between the instructions, between the two compilers, and also between the instructions and the statements of the source code. But unfortunately, we don't have this. Maybe we could use some kind of debug information to derive this, but that would likely not work in most non-trivial cases. So what we want is, we want to do differential testing. We want to compare these two outputs and figure out the difference. And for this, ideally, as before, we would need something like this. The mapping between here are the if statements and the compiler or the assembly instructions, so that we can do this comparison easily. Here, I just highlighted this by hand, but the question is, how do we do this automatically? Well, the answer is we don't, because it's a very difficult problem. Instead, we try to solve a simpler one that can help us infer this relationship. So what we do is, we don't compile the original program, but we add what we call markers that can help us derive this relationship. So in this case, we add these markers in if statements, and these are calls to functions that have only been declared and not defined. So the compiler only knows their names and their types, and it cannot analyze them, it cannot inline them. So the only way that these are eliminated in this case is if the compiler figures out that these two statements are dead. So their conditions are always false, and therefore they can never be executed. And now if we look at the output of GCC, we see the two markers there. And it's now very easy to figure this out just by searching for these names in the assembly code. And similarly, we do the same for LLVM, and we see that there's one marker. And now the differential testing is extremely easy. We grep or we search for the markers in the assembly code, and then we check which ones have survived in both compilers. So the length of that code elimination is the following. We take a piece of code, we instrument it with markers, we use 2 or more compilers to generate assembly code, and then we check which markers are alive in both compilers, or in the outputs of both compilers. Is there a difference? In this case, there is, so we have found a missed optimization. So in the examples up to now, I've just used GCC and LLVM, but we are really flexible in what we can use for the two compilers. We could use, for example, LLVM 13 and 14 if we want to find regressions, or LLVM at 01 and 03 if we want to find cases where 01 is doing a better job than 03. Or we could have a difference of a single commit. So one compiler could be the main branch, and the other could be the main branch plus the commit that we are working on and we want to test. And this is the core idea of how we find missed optimizations, but there are a few steps missing. This is not an end-to-end automated approach. We want something that just searches and generates really small test cases, such as the example I showed before, so a few lines of C code. And to build the end-to-end pipeline, we relied a lot on the tools that are from the testing community. And the first piece that we need is input code to do our testing. And for this, we use Csmith. So Csmith is a program that randomly generates C code. And the C code that it generates contains a lot of constructs, like a lot of control flow constructs, like loops, if statements. There's also arithmetic, function calls, and so on. So it's a full-blown program. It's just randomly generated. And it can be a few hundred or even a few thousand lines long. So now that we have our input test case, we just need to instrument it. And we do this by inserting markers in roughly places that correspond to basic blocks where the control flow of a program changes. And the way we implemented this was with lib tooling. And essentially, we work on the Clang AST and insert the calls in the right locations. So now that we have our instrumented candidate, we can do differential testing. We take one compiler, say LLVM 13 at 03. We check which markers are still alive. We use the second compiler, say LLVM 14, and we check which markers are alive. So now we have observed a difference, so we have found an interesting candidate. So we have found a missed optimization. And this is the output, essentially. For a given instrumented input and the number of compilers that we are testing, we are trying to find if there are certain markers that are missed. If we hadn't found a difference, we would just continue looping until we find one. So that's our test case that demonstrates the missed optimization. So for a given piece of source code and two compilers, we know that one is missing something. The problem here is that we have a very big test case. We have several hundred or several thousands of lines of C code. And obviously, this is not something that's easy to understand or actionable. We cannot report such a thing. So what we need is a smaller version of this that has the same property, so this difference in missed markers. And for this, we use C-reduce. which is another tool from the testing community that essentially tries to remove chunks from the program while still maintaining property of interest. In our case, the property of interest is the difference in missed markers for the two compilers. We also care about correctness, so the reduced program shouldn't contain undefined behavior or other such problems, so we also use certain tools to help us ensure that this is the case. And now the output is this. So in this test case, the problem is that LLVM 14 cannot remove the last marker, so if BDC marker 8. This call. And we can verify that this is the case by just running the two compilers. So if we run it with LLVM 13 at 03, we see that the output is this one, so these 5 instructions. And now if we run it with 14, we see that, well, something must have gone wrong. Now the compiler has generated 5 times as many instructions, so it probably cannot simplify something. And this is the whole pipeline for finding such reduced test cases. But since we're dealing with a regression here, we can take one more step. We can find the commit that caused this problem. And we do this by bisecting on the compiler's history, or Git history. And if we look at the title of the commit, this seems to be related to some inst combine rule, and also with negations. And this is exactly what we see in the test case. So we have here short C equals -A, and so on and so forth. So we can essentially use this tool to find also the commits that cause the regressions. And this is the complete pipeline that we have also implemented on our tool DED, which stands for Dead Code Elimination-Based Automatic Differential Testing. And it's available on GitHub for anyone to use. And I would be very happy to help anyone who wants to use it or to implement use cases that are not supported yet that you would like to see. And generally, any feedback, positive or negative, would be very welcome. So as I mentioned, we reported a number of cases, and the problem that we have now is that we have a backlog of a few hundred such regressions that I showed, and I'm not really sure what's the best way to handle this. I guess flooding the bug tracker would not be nice, because a lot of people would get annoyed by that. So if you have any ideas of how to handle this, also please reach out or send me an email. So up to now, I described how we can use this idea to find bugs, but we can also use DCE to study compilers. We can see how well they're optimizing code through the lens of dead code elimination. And the simplest question that we can ask is, how good are compilers at eliminating dead code? And for this, we use the corpus of around 10,000 CSmith programs. And CSmith programs are quite good for this because by design, they contain a lot of dead code. And in our case, it was around 3 million dead blocks. And now using both GCC and LLVM, we just tried the different optimization levels. How many of the dead blocks are missed? And unsurprisingly, the higher the optimization level, the better. But still, both compilers are missing around 5% of the cases. Obviously, we cannot expect this to be 0, because some of these would likely require too much of an effort from the compiler to prove dead, or maybe they require solving a halting problem or whatever. So 100% is not the target, but definitely there is room for improvement. But then the next question is whether what we are proposing, this DCE-based testing, feasible. Can we find differences between the two compilers? So cases where one compiler eliminates a piece of dead code and the other doesn't. And the answer is yes. For example, we find around 40,000 dead blocks that LLVM eliminates, but not GCC. But also there are a few thousand in the other way around, meaning that there's no clear winner. So both compilers can learn from each other. But we can also do this with a single compiler by testing different optimization levels. So we have a number of cases where O1 or O2 can eliminate something that O3 fails to do so. And this shows that we can use the lower optimization levels to find what we need to teach to the higher ones. But the other question we can also ask is, how well are compilers evolving? So here we checked LLVM 4 through trunk, and in this case, trunk is a bit older than the branch point of LLVM 14, so a few weeks older. And we checked what percentage of dead blocks are being eliminated at each version. And as we see, the numbers are getting better and better, so the compilers are getting better and better, so I guess that's good news. But at the same time, we can ask the other question, are there any regressions? So for each compiler version, what percentage of dead blocks are missed but were previously eliminated by at least one other compiler? And it's always a few percent of the cases. So version 4 is at 0 simply because we didn't have a previous version, and that's where we started. But I'm pretty sure that if we had also tested 3, we would find a few percent there as well. And the latest, if we look at the latest versions, then we see that this number has somehow converged at 4%, but the important thing is that these are not the same 4%. For example, between 13 and trunk, around a third of these regressions are new. And what this means is that even though overall the compiler is getting better and better, sometimes it somehow misses always some new things. So this is maybe another highlight why we need automated testing to catch these issues and prevent them. So let's look at a few examples that, of the kinds of issues that we can find. So even though this is EuroLLVM, I will start with a GCC one, because in my opinion, it's a bit interesting. So what we have here is a case where we have a marker that is dead, and GCC at 01 could eliminate it, but at 03 it couldn't. And what we have in this test case is in the if statement, we check whether the entry of the first entry of RAC points to a non-zero address. And, or actually, if it points to a 0, to the null pointer. And in fact, it is not, because it is initialized in the above loop with some constant address. But the problem was that at 03, this loop got vectorized. And the way GCC vectorizes pointer data, and in this case, this C star array is pointer data, is by using unsigned integers. But the type of these arrays were signed integers. And therefore, whatever knowledge was derived in the vectorized loop, because there was this type mismatch, it couldn't be propagated later on in scalar uses of the RAC. So this should be fixed in the current version, but we really see how we can find obscure cases just by, or not obscure cases, but cases between 01 and 03, where 01 somehow ends up doing a better job than 03. And similarly, we can do the same for LLVM as well. So again, the marker was eliminated at 01, but not at 03. And what happened here was that the compiler could simplify all the arithmetic, and then what it would figure out at 03 is that the arguments of this modulo operator there were ranges, constant ranges of a single element. So the length of these ranges is 1. But the problem was that it wouldn't simplify this. Even though it's quite, I mean, if you do the math, you can see that it's quite easy to simplify. And this was really an omission, because similar simplifications existed for other binary operators, such as logical AND, but somehow modulo was forgotten. And this is yet another example on how we can use a lower optimization level to figure out what the compiler already knows, but somehow at 03 it gets stuck. So we can use this to find such cases. And we can also find regressions. So what we have in this case is a problem where sometime between LLVM 13 and 14, the compiler stopped being able to eliminate this marker, but the development branch, this was, I don't remember exactly when, but a few months ago, regressed. And we had a regression in the peephole optimizations, in shifts actually. And the commit that caused this regression was actually a commit that tried to introduce new inst combine rules for shift operations. So this is, I think, yet again a highlight that we need a way to catch these before they land into the compiler, because it is really possible to automatically find such issues. And we can even find very old regressions. For example, here we have one where LLVM 4 is able to eliminate a piece of code. and O3, but the main branch cannot. And here the main branch, well, at least the main branch until a few days ago. And if you look at the code, and if you spend 2 minutes here, we can really see how it really makes sense that the marker is dead. But somehow this regression was caused by a commit that, and if we look for it, it looks like this. And if you read the commit message, you can see that what this commit was trying to do was to fix some other optimization issue. But it somehow ended up causing a new one. So yet another highlight of why we need automated testing to catch these problems. So up to now, what I have described is a way to use dead code elimination to find problems in compilers or in the optimization pipeline. And the reason that we can use this is because DC, as I explained, interacts with many compiler components. So the way that that other optimizations or the quality of other optimizations can affect the quality of DC, and at the same time, DC can affect the quality of other optimizations. And the thing is that a compiler is a very complex piece of software. It contains hundreds of different components that have to interact with each other. There's no way that DC is the only one that leaks information in this manner where we can very easily check the outputs of two compilers and deduce that one is doing a better job. So in this case, we know that if a piece of dead code is not eliminated, there's no reason why a compiler shouldn't eliminate it. So the question is, what are these other components that we can use? And potentially cover a larger surface area of a compiler by using these. And maybe this could be some sort of analysis. I could imagine, for example, that we check what is the value range analysis outputs of a compiler. So if compiler A believes that an integer variable takes values from 1 to 5, and another compiler thinks that it takes values from 1 to 10, since the first compiler is more precise, then maybe it is doing a better job. But the question is, what are these other components? Or maybe how can we slightly modify parts of a compiler that can emit such useful information that we can use for automated testing? If you have any ideas, again, please reach out. I would be very happy to discuss and potentially collaborate on this, as I guess we're all interested in finding such problems in compilers. But then there are other components that don't really interact with DC in any meaningful way that we can use, for especially stuff towards the backend, like register allocation or auto-vectorization. And there was an example for GCC with auto-vectorization where we found an issue, but this was an indirect catch. We're not directly targeting these kinds of transformations or optimizations. And the problem here is that, or what we would like to have is some way, given, say, a function or a loop nest, and a vectorization scheme or a register allocation scheme, a way to do this comparison, this absolute comparison where we say that one scheme is strictly better than the other. Obviously, this cannot be done in the general case, but maybe there are special cases where this is possible or special applications where this is possible. Maybe, for example, for when we generate GPU code. Or maybe other more complicated cases can be reduced down to this. So again, if you have any ideas, please feel free to reach out, and I would be very happy to discuss. So, to sum up, today I have presented a new approach for finding missed optimizations and regressions in compilers, and we have, as I said, this tool is available on GitHub, so please feel free to use it and give us any feedback, because we're really interested in how we can continue developing this and what directions or what features are actually needed by compiler developers, because from our point of view, the researchers, we don't really we don't know what happens behind the lines and what are the actual features that you need. But with this work, our goal was to fill in a gap in the tooling that is useful for developing compilers and making sure that the optimizations that are in them work, at least don't work in unexpected ways. But at the same time, when it's obvious that there's a lot of open questions and a lot of additional research that needs to be done. As I'm pretty sure we have only scratched the surface, and now the question is how do we expand this to cover more interesting cases that we cannot nowadays. So there's, I guess, a lot of exciting work to be done. And I think now I'm open to take questions.
Thank you for your talks. I think this is really useful tool, I guess. But could you go back to your example, I think maybe page 10.
Page 10. Wait. Page 10. This one.
Yeah. So I think there is a undefined behavior because the integer a, it is a external visible variable. So I think GCC.
Sorry, can you explain this again? It's what is a?
So the integer a, it is a global visible variable.
Yes.
So that means if b a, I would say.
Okay. So this a should be static. You're right. It's missing from the. It should be static in int a.
Okay.
There's a typo in the slide.
Okay. Okay. Thank you.
Well, thank you for this work. I was wondering, how do you ensure markers do not influence in optimization opportunities?
Sorry, again, I cannot hear you because I think the speakers
okay.
are...
How do you make sure markers do not influence optimization opportunities?
So they definitely do. They change what the compiler can optimize. Because suddenly we have I mean, you can really see this here. That's how LLVM's output suddenly becomes much larger. And we know that they are affecting how well a compiler, or what a compiler can do, but this doesn't invalidate the result. We can still find interesting missed optimizations or regressions. But for sure, they are changing what the compiler's output, and maybe they're blocking certain optimizations.
Thank you.
Hey, thanks for the talk. So I was kind of curious if you considered, so like from what I understand, this is essentially always like differential testing, like you take two compilers, you make sure they essentially, stay up to date with the same optimizations. But I guess if you want to work towards like this, perfect compiler, we have like, higher goals than GCC and Clang. So I was kind of wondering if we maybe have some other ways to find like that code. Like, for example, I think the program has no input, so you could run it and see what's actually executed. And you could start arguing for there, like what's the, ideal that code elimination that we would have.
So let me find the slide. So here, here. To get these numbers, we did exactly what you're describing. So we ran the code to find which pieces are actually dead. The problem with this is that if you do this with generic code, it's a bit difficult. But the nice thing with Csmith programs is that they're closed, so they don't take any arguments, and they're deterministic. So you can very easily figure out what parts are dead and what parts are alive, and you can do this. If we take now any piece of code, I'm not sure to what extent we can do this. Maybe we could use something more powerful like a Z3 solver, and then we don't care how much time it takes to prove that parts of the code are dead, but we didn't do anything like this.
Thanks.
But
still very
it's
cool.
Definitely a possibility.
Right, that's very interesting presentation. I can go back to a page, you compare across multiple LLVM versions, the percentage from 67% to 96%. something like that. Yeah, this one. May I understand what does 100% means? What is the baseline here?
What is the baseline?
Yes, what is the baseline?
So
if
the
100%, what does it mean? Yeah.
So what this means is that if we look at all the dead blocks, so we know that 100% is dead. So it's actually the same thing that you see here. So we know the ground truth. We know which blocks are dead. And then we try to ask the question, how many of these is the compiler actually eliminating? So in this case, trunk there are 4% of dead blocks that have not been eliminated.
Right. Then how could you have an automatic way to figure out that they should be dead? How did you do that?
So exactly, we run the code to figure out, because the nice thing with these programs is that if we run them, we can really figure out what are dead, what pieces are dead, since the control flow is static, it doesn't change.
Thank you for this talk. It was very, very interesting. My question is about, you say you generate 10,000 test programs. Mm-hmm. How long does it take to run all the testing? Like,
so
we're talking about hours.
So essentially, how long does it take to do all of this?
Yes.
That depends. So the first part, until like generating a candidate and doing the check, takes a few seconds.
Okay.
So not really, because so maybe a bit more, because when we generate this, can I point somehow? This candidate, we also need to make sure that it doesn't contain undefined behavior or is problematic, because sometimes Sysmith can generate programs that don't behave that nice. So we need to try a few times until we find one that behaves nicely. And then once we have this, we need to do all the rest. So if I run the program now on a fairly large machine, let's say a 64-core machine, between LLVM 13 and 14, within an hour, I will definitely find a few such cases. But the individual one really depends on how many we have found already, because what we do is for example, for regressions, we have a database of what we have found, and we are only interested in finding new ones, not ones that have already been found. And then over time, this gets more difficult and more difficult. But I would say that if you're testing against a very different compiler like a GCC, then you can find this very easily and really fast.
But you say few seconds per candidate, or few seconds?
So, I mean, testing a candidate takes a few seconds, but finding an interesting one is a bit slower. It can take minutes or tens of minutes or an hour. Okay. Especially if we are testing, let's say, a single commit. Maybe it's really difficult to find a problematic case, if such a case can be found.
So you're, sorry to go on, but so 10,000 candidates means?
Okay, you mean for this thing?
Yeah, I mean, how long, okay. How long does it take to do all of it?
Oh, like, for this? So on a 64-core machine, less than an hour.
Okay.
Okay. At least that's what I tried. So because there's a lot of parallelism here, so you can use as many cores as you want to do this.
Perfect. Thanks. So first suggestion, you ask how you can make generate output that doesn't, for instance, change the result of the compiler, because inserting functions will change how inlining works, etc. One thing you can do, and you can do on both GCC and LLVM, is output assembly comments with specific tags. So you just change the backends or the ASM printers. It's a hard work, because you have to do for a lot of them. But if you have like markers in the assembly comments, then you can track this without changing the source code.
Interesting.
And you need some kind of generic language that both GCC and LLVM follow, so that you can track in the same way. So it's hard work, but it won't change the source, right?
Yeah, well, ideally, we would have some common IR where we can do all of this, but that would be quite a lot of engineering effort to implement.
The question I have for you is, when you generate these tests and you find these problems, and say you fix the problem, right? And then a good idea would be to get this IR or this test that you have and put in the LLVM test suite, so that the next person that is going to work on inst combine doesn't break it. But the probability that the next breakage is going to be on the same thing that you found in a randomly generated program is very slow.
So,
very small. So how do you make sure that you actually get all of the cases that will happen in the future?
So like up to now, what we've been doing is we reported this, and then the developer was including a test case. But back to your comment about the probability being very slow, we have it has already happened that we reported something, it got fixed, and then we reported something else, and then it broke the original thing that was reported. So I think there are certain components that are very fragile, and a lot of these were inst combined, for example, rules, but not only. And yeah, I'm not sure what's the best way. Maybe it makes sense to generate just a large benchmark or test suite out of this, and then give it to upload it somewhere online so that people can test against. But yeah, as I said, I'm not sure what's the best way.
Thanks. So actually related to that one comment where you had something break what you had fixed before, have you had any instance where it's an actual trade-off so that you either can eliminate this or that, but not both? Or do you think there's always a way to get rid of all of them?
I'm not sure, but the kinds of test cases that we found, we can see that there's always something that can be eliminated because we have an example of another compiler, or even the same compiler at a lower optimization level. Now, if there are cases where either one or the other can be eliminated, I haven't seen one, and I cannot think of an example. Maybe there is, but we haven't looked into that.
Okay, I think we have time for one more question.
Yeah, thank you for the talk. As you said, if you report such an example, you always have an example of a compiler that is able to optimize correctly and the other compiler is not. Among those 10,000 test cases, have you found any, like a core of programs that is notoriously hard to optimize, like where none of the compilers is able to optimize correctly?
Yes. And for example, for these numbers, what we have here is we filtered out all of these test cases to generate these percentages. That's one example. The problem is that there are definitely cases where no compiler at any version or optimization level can eliminate this piece of dead code. But what is very difficult to judge is whether this is just some miss case that nobody has thought about, or it's something that is inherently difficult. Because it's, yeah, you would need to solve some NP-hard problem in order to prove that a piece of code is dead. We generally ignore this, as we are not sure if it makes sense to report such problems or spend time with this, but maybe there's something to be done there in future work. But up to now, we just ignored those issues.
Great. Well, let's thank our keynote speaker.